Today you're here for a quick and dirty introduction to Git. But first, credit where credit is due. This presentation is largely based on Alan Ott's excellent Git Like You Mean It presentation from Scale 16x. Heavily edited for time constraints. I urge you to view his presentation because he delivers it much more eloquently than I can even hope to. So, who am I? If you ask my private brain care specialist, he's just his guy, you know. Seriously though, my name is Donald Burr. I have been working with technology since, I don't know, like I was three years old. And my parents used to love it when I took apart everything in the house and usually not successfully put it back together. I've been working with Linux and FOSS software since the bad old days. My first vivid memory is sitting with a friend in his cramped apartment installing Slackware from floppy disks. And it was an insane amount of floppy disks. I forget how many, but yeah, fun times, fun times. Mac Windows, Linux, GPL, BSD, not even going to go there. Just use whatever is the tool that suits you the best. That's what I say. And finally, I am currently a senior software engineer at VCT Labs. We're a small consulting outfit in Santa Barbara. We do just about everything. Check out our website, which is in need of work. That's my next project. And I apologize if I don't make eye contact with you because I am extremely nearsighted and I just squint down at my computer, so it's nothing personal. All right, so overview of SCM, aka Source Code Management. It encompasses the tools and methods for doing revision control of software. Generally speaking, you're talking about a centralized repository, which is sort of the authoritative source. Developers commit source code changes to that repository. A log is maintained of all changes, and branching and tagging is supported. And the central server is usually the authoritative source. The systems that we're probably familiar with the old way are CVS and Subversion, which is most definitely a centralized model. Your repository exists on the server. Each user has a working copy that they check out. They commit changes from their working copies to the server, and the history is maintained on the server. Well, this is great. It's easy to understand, classic client-server, but it has some disadvantages. It's very hard to preview commits. So once a commit is made, that's it, they're immutable. So if you screw up, well, usually you have to make a second commit. Oops, forgot X, you know. And anything involving the log must fetch everything from the server, and it's really, really, really slow. More drawbacks, any kind of branching or merging involves going to the server. Again, really, really slow, and there's no concept of local branches. And switching branches in particular is also very slow because you have to go up to the server and pull down whatever branch you're switching to. Merging is very difficult, varies by system. It's been getting better, but it's still pretty onerous. And finally, Subversion in particular lacks the support of tags. Instead, most developers do this sort of convoluted system. They create a directory called tags, and whenever they want to tag a release, they literally copy the entire stuff into a named directory in the tags directory. So it's pretty kludgy. Now, distributed SCM. It's a distributed system where each user has a full copy of the repository, including all the history, tags, branches, the whole enchilada. And when you're what's called clone from the remote repository, both the remote and your new clone start out identical. All the functionality of the remote repository is available on the local repository. You can make local branches, you can tag stuff locally, you can commit stuff locally, so on and so forth. And a local repository can even track multiple remote repositories, which we'll get into more later. This is great. I can commit code while I'm on the train. That's true, but believe me, it's just the tip of the iceberg. This is great. I can look at the log. I can look at the log while I'm on the train. Also true, but I mean, it's just because looking at the log can be done offline. It's fast and much more useful, even when you're not on the train. This is great. I can create, switch to, and merge branches. Well, maybe I should move closer to work. It's not really about the train, really. It's about all the other implications of being able to work locally. What are they? Since history is convenient and fast, there's potential for history to actually be useful. If history is going to be used, it's important that history be clean. First of all, linear. You don't want one commit to depend on a later commit, because if that case happens, then the earlier commit is broken. You also want concise commits, germane to one thing. You don't want one commit that adds like every single 5 new features. I call them kitchen sink commits. They're pretty gnarly. How do we create this? Well, let's look at the old way. SVN and CVS, all commits are final. The documentation says, well, if you need to change something, just make another commit. Done. Well, it works, yeah, but wouldn't it be better to just get it right the first time? And CVS and Subversion does not contain a mechanism for that. So let's see some examples of the badness. Okay, so, all right, so commit 612 up here. Integration fixes from redacted facility. Well, that indicates to me that that's one of those giant commits that includes like just about everything under the sun. A kitchen sink commit. Well, yeah, that's a big mess. Then if you look at these down here, these 2 commits, bump version 2352, exact same commit message, probably means that the second commit up here is because I forgot something and had to add it in a second commit, but that means the first commit is likely broken. Another example of that here in commit 448, updated version 124, and then right after we have a commit, oops, yeah, commits with too many things combined, and oops commits bad. And more limitation. When you commit, committing code in Subversion's SVN commit, file 1, file 2, blah 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 blah. What if you forget one? What if you have some debug code in there that you don't want to commit? What if you screw up the commit message? There's really no way to go back and fix it. You have to do one of those oops commits. So how does Git handle this? Well, in Git, we provide tools to address these issues. Local history is editable, which means once you commit something, it's not quite set in stone until you push over back to the remote repository. You can feel free to edit, fix things. And also, Git has a separate add and commit procedure. Means it's easy to review what's being committed before you actually commit it. This means you can do small atomic commits, and it means it's easy to create a linear history, where one commit doesn't depend on a future commit. And if you mess up, you can go back and fix it. And once you're satisfied that it's all right, then you push it off to the remote repository. So, great. We can clean up the history. We can. Who really cares? Who cares? Well, you should care, because it makes small, clean commits make code review possible. It means you can have problems are harder to introduce. There's fewer unintended consequences. And it also makes bisection possible, which is really cool, and we'll talk about that later, time permitting. And all of the above contribute to better code quality. So let's talk basic Git tasks. To create a Git repository, go into your source directory and run the command git init. Creates a directory .git. That's where the actual repository stuff is. The actual files in the current directory are your working copy. And when you create a repository, no files are committed automatically. You have to do that yourself. To add files, just git add file spec. You can use wildcards, whatever. This adds a file to the index. Git has three sort of working areas. There's the working copy, that's the directory where all your source code that you're working on lives. There's the repository where all the Git stuff lives. And then there's this zone in between called the staging area. I like to call it code purgatory. It's where your commits go and wait it's where when you add files to a commit, they just sort of go there and sit there until you're ready to commit them. Yeah, so when you add a file, it's not committed, but it's staged for commit. Git add can be run multiple times to stage commits from multiple files for a single commit. And to actually commit it, you do git commit. This creates a commit containing all of the changes which are in the staging area. It'll open your editor to ask you, you type in your commit message, blah, blah, blah. And once you save and quit, it's committed. After running the previous command, your repo has a single commit. You can view your commits with git log. This opens up the log in less. You can use up and down arrows. You can scroll and press Q to exit. You can also view the diffs that each commit contains if you give the -p argument. After the initial commit, you'll probably change and add code, do normal development. At any time, you can show the status of the working directory using git status. It shows any files that you've added, changed, or removed. It shows any conflicts if they exist. And it also shows any files that are staged for commit. To show everything that's been changed in the working copy, do a git diff. And this shows a colorized diff, and you can page it with less. It's really cool, really handy. At some point, you'll have multiple commits worth of stuff in your working copy. You've been hacking on code for a while, and you fixed 3 or 4 bugs. You've added some things. So you have a bunch of changes in the working copy that you want to commit. But again, you want to try to keep your commits small and germane. So you can actually stage individual changes in each file using the git add -p. This will literally go through all your files that are changed. It'll show what you changed, and it'll ask you what to do with it. Do you want to stage it? Do you want to not stage it as part of this commit, and so on and so forth. Once you've added all the diff chunks for a commit that you want, once you've added everything that you want in that commit, you should review them using git diff -cached, which shows the difference between the repository state and what's in the staging area. This will show you all the changes staged for commit. It's important to do this review. Sometimes you can confuse yourself. Maybe you added something that you shouldn't have. You can always go back and fix it. And if there's something you don't like, you can change it. To make the change, you can actually change your working copy and then run git add -p again, and it'll update the index or the staging area. To remove changes in a file, you run git reset head and the file name. This basically removes all changes from the file name. This basically removes all changes for the file name from the index. Once you've reviewed your changes, you can commit them with git commit. This will create a single commit. It'll pop up your editor and ask you for a commit message, which we'll see in a moment. Now that you've made a commit, run git log, and you'll look at it. You can see it. Make sure it looks the way you want it to. And it makes it easy. Your commit message will be intended by 4 characters. And of course, checking your work is always important. So if the commit message is not right, maybe you made a typo, maybe you left something out, you can easily change it with git commit-amend. This will edit the log message of the topmost commit, which is called head. And other commit messages, you can actually change other commit messages as well using Rebase, which hopefully we'll get a chance to get into later. So you made your first commit. Run git diff again to see the remaining changes and iterate until finished. Lather, rinse, repeat. To get more information, you can always do git status at any time. This will tell you changes in the working copy, changes stages for commit, and how to revert changes if that's what you really want to do. Commit messages, Git has a de facto standard for them. The first line is the summary line. It's always displayed. There's two ways of viewing Git logs. You can either view the full log, or you can do what's called a one-line log. And if you look at a one-line log, all you see is the first line. So that should be basically a concise summary of what that commit contains. And there's sort of a de facto standard for them. You put the subsystem, whatever subsystem that commit affects, followed by colon, and then a short description of what the commit entails. Follow that with a blank line, and then you can put in a longer description. And when I say long, I mean long. You're not really limited in any form other than disk space, which is plentiful. This is a great place to describe in excruciating detail what your change is about, and it's great for documentation. If I'm working with coworkers, like in a Slack or something, a lot of times I paste in the Slack logs. It's really cool. And when you're talking, you really should use the imperative mood, which is basically commands. Change X, add support for Y, handle exception in Z or Z, depending on your nationality. Don't use sort of this patch does this. It's that whole sort of passive voice thing that your English teacher drummed into you. So here's a sample commit message. The first line is the SHA1 hash of the commit. It's basically a hash of everything in that commit: patch, date, time, author, email, blah, 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 including the hash of the previous commit. This commit ID serves as a unique identifier of this particular point in the history. It identifies the specific commit, and since it also includes the hash of the previous commit, it also identifies indirectly the branch that this is on. The commit ID is used everywhere in Git where it asks for a revision, and you'll see that in the Git documentation. A lot of commands ask for revision as an option. Well, you can give these SHA hashes, and you don't have to type in the entire long hash. You just need to use enough characters to where it's unique across that repository. In general, usually using only the first 6 to 8 characters is fine and a lot easier to do. You can also use it with git checkout to check out a particular point in history. So git checkout the hash or whatever. It'll check out a specific version to the working copy. Next, we have the author and the date. One particular note is that the date shown here is the date of the commit, not the date that it was merged or pushed to a remote repository. So that means new commits can potentially have old dates. So dates are not necessarily increasing, and commit dates are not a good way of determining the state of the repository on a particular date. Next, we have the summary line. Again, the summary line and the long description. Again, subsystem colon, brief description, and then a blank line, and then go hog wild. And I have a formatting error. Oops. So yeah, you can definitely put more info in the long description, and more importantly, you can reference other commit IDs in that description. And in many cases, like if you're looking at a repository on an online service like GitHub or GitLab, they will turn those into clickable links so that you can just literally click and see what commit that you're referring to, which is pretty cool. So The interactive demo, I'm going to defer the demos until later. Hopefully we'll have time, but if not, check out Alan's presentation because he goes into exhaustive detail. All right, now let's talk about ranges. Some Git commands can take a range parameter. For example, you might want to look at the differences between two different commits. For example, git diff shall, and the way you specify a range is something dot dot something else. So that something can be SHA hashes, it can be branch names, it can be tags. We'll talk more about that later. This basically shows all the differences between the two revisions that you gave it. The same can be done with git log. It'll show all log messages. It shows a log of all the commits which are in that range. Remember, in general, ranges are older dot dot newer. Excuse me. You can also use symbolic names, meaning the name of a branch or tag. So, like if you have a release tagged as 4.13 and 4.14, and you want to see the differences between the two, you can do that. One revision has a special name, head. Head describes the most recent version which is checked out in your current branch. And this is useful because sometimes you might want to get a log or diff from some revision to head. So, if you wanted the differences, 4.14 and head, that's how you do it. You can also reference a commit previous to a specified revision. Usually this is just done using head. So for example, putting a caret after a revision gets the revision previous to the specified revision. So if you do git log head caret dot dot head, that basically shows the most recent commit. And you can use multiple carets to go even further back in time. So git log head caret dot dot head gets you the last 4 commits. That can be kind of awkward, so there's also another alternate syntax. You can do head, with a tilde and a number, which indicates the number of commits to go back. So git log head tilde 4 dot dot head is equivalent to git log head caret dot head. As a shortcut, the last revision can be omitted and head is implied. So git log head tilde 4 is the same as git log head tilde 4 dot dot head. And check out the man page for more information. Branches and merging. This is really important stuff. Remember that in a distributed SCM like Git, the entire repository exists on your workstation, which includes branches and tags. And that means you can make branches locally, which do not correspond to upstream. Branches are really, really fast to create and fast to switch between. Very convenient to create local feature branches where you can do work on. Git will always give you a default branch called master. Typically, this is the branch that's synced with the upstream. It's basically equivalent to trunk in SVN. There's nothing really special about the mechanism of master. Git's not going to enforce anything regarding that, but generally this is the sort of the de facto way of doing it. To view local branches, just run git branch. Whatever branch you're currently on will be indicated with an asterisk. To create a branch, you can do git branch name. Pretty simple. However, note that when you create a branch, you're not automatically switched to that branch. To do that, you use git checkout. So checking out a branch checks out the branch to the working copy. working copy will contain the branch. The log will reflect the branch that's currently checked out. And when you commit, it'll be made to that branch. You can easily switch between branches using git checkout. Make sure to commit your changes beforehand, otherwise Git will complain. So it's convenient to use branches to work on a feature. Make a branch, check it out, do work on feature X, commit your changes. Then when you're ready to merge those in, you check out master, and then you merge your feature branch in using git merge. Hopefully your branch can be merged. If not, Git will often tell you in great detail what needs to be done to make it happen. Sometimes you'll have conflicts, and conflicts work similar to how they work in CVS and Subversion. And hopefully I'll have time to get to the branching demo. Right, now let's talk about revisions. So you can check out branches, but you can also check out other things. You can check out a specific revision, aka SHA1 hash. You can check out a specific tag. You can check out branches. This makes it very easy to work with older revisions. When switching between revisions with Git, sometimes there'll be conflicts, and in that case, Git checkout will refuse to alter the working tree, and it'll warn you. Now, if you really want to check out that branch, you can do something called stashing. This is pretty cool. Basically, Git is able to store away all of your working directory changes into a sort of holding area called a stash. There's also hard mode, which I call the nuclear option, because it resets the commit history, but also resets the working tree. And be very careful with this, because if you have any unsaved changes, it will wipe them out. Hence why I call it the nuclear option. There's also git reset soft, which it resets the commit history, but it leaves the changes and puts them in the index, basically in the staging area. And the man page for git reset describes all of that in greater detail. Now, rebasing. And this is the concept that I found really hard to wrap my brain around for the longest time. But it's really powerful. Probably the single greatest feature, in fact. Remember that in Git, the history is editable. So this might seem scary, but really it's not. It's a huge benefit. Remember that your history in distributed systems like Git is local. So, that is to say commits which are not yet pushed to remote. You can usually edit local history before it is pushed to a remote repository. Basically, this is a way of getting it right before you send it off to the world. So what is rebasing? There's two kinds of rebasing. We'll first talk about simple rebasing. Simple rebasing involves inserting commits from another branch or upstream before your local commits. So for example, you checked out some code, you've got a working branch, you've done some stuff, made some commits. Meanwhile, back at the ranch, someone else has pushed commits to the remote repository. However, when that happens, you want your commits to be on top of the remote commits. So here's a little example. The state before you started work just has a master branch. It contains the main line of development. It has some stuff, potentially fast moving. So you check out you create a working branch. This is on your workstation, and you make branch local commits to it. However, meanwhile, commits are made to the master branch, maybe from upstream, maybe from other developers, which means that master and your working branch now have diverged. And so if you want your commits to the working branch to go up to master, you might have some conflicts, and you'll have to work on removing those. That's what git rebase does. Basically, it pops your branch local commits out of the history and saves them. It applies the commits from master to the working branch and reapplies your saved branch local commits to the working branch. So the name is appropriate because it rebases your local stuff. So here's the basic workflow on that. You check it out, you do some stuff, and then meanwhile other people are doing stuff to master. When you're ready to you check out master and you pull from master, which means get the changes from the remote repository, and then you check out your working branch again and you git rebase master. And what it does is it saves all your commits, which are in the working branch, but not in master, to a temporary area. It resets the working branch to the most recent commit, which is common to both your working branch and the master. It applies all the commits from master, which are not in your working branch, and then it applies your saved commits from your working branch. Of course, this means you could come into conflict. Maybe you were modifying something that someone else did. In this case, Rebase will stop and give you an opportunity to fix it. At this point, you can run rebase-abort, which cancel, and that basically reverts back to before your rebase attempt. Or you can fix the commit and run git rebase-continue. If a conflict or exception cases occur, remember that a lot of times Git will tell you what to do. And running git status is a good way of finding out what needs to be done. It basically, and one thing I find helpful is opening a second window. That way you can have one window where you're working on resolving the conflicts, but you have the second window where you have your status message, so you can always see what needs to be done. Really handy. And another demo, which we hope we'll have a chance to get to. Now, the second type of rebasing is interactive rebasing. So simple rebasing, which is what we just finished talking about, is used to integrate the history of one branch into another branch. History is rewritten. With interactive rebasing, it also rewrites history, but it's a lot more flexible. Remember, of course, that rebasing should only be done in local branches which are not pushed yet to remote. Interactive rebasing is really cool. It allows you to dramatically rewrite history. Of course, again, only do this on a local working branch. Do not rebase commits that have been pushed to a remote repository. Use Rebase to integrate changes. One great use of interactive rebasing is to use it to integrate changes that were suggested during code review. and this can happen before a branch is merged to master. So rewriting history is important during the development process because, first of all, you want your history to be as simple as possible, meaning, simple commits. You don't want those kitchen sink commits that include basically everything under the sun, like I talked about. You want to make commits linear. Each commit builds on a previous commit. Commits don't undo one another, and there's no oops commits. Just rebase and fix them. And again, your goal is to make every point in history valid. No commit should break the build. So to start, you run git rebase-I followed by a revision, which will rebase all commits newer than said revision. And when you do this, Git will open up an editor window with a list of commits, one per line. Each line indicates what to do with. You use the editor to specify for each line what to do with the commit and the SHA-1 and the commit message. From this window, you can delete a commit just by deleting the line. Be very careful because it literally will wipe that commit off the face of the planet. You can reorder commits, literally just moving lines around, copy paste. You can modify the commits. You can edit by editing the first word of the line. The file has a little comment section that tells you exactly what you can do. The most used commands, P for pick, which basically leaves that commit as is, which is the default. R for reword, lets you change the commit message. E for edit, lets you change a commit. And S for squash, lets you basically combine one commit with the previous commit. There are more things you can do. They're kind of, in general, used a little less frequently, and we'll read more about it in the little comments section in the editor when you rebase. So easy to move commits around. Of course, there's a problem when you get a conflict. Again, it's just the normal conflict resolution stuff. You'll be able to resolve the conflicts manually. Be careful when editing the rebase command file. Deleting a line will literally remove that commit from the face of the planet. Again, I find it really helpful to have multiple windows for this, because in one window you have the rebase command file, or the rebase command line, because it'll stop either for an error or for editing, and it'll tell you the next steps. So I like to leave a window open for that, and then have a second window to do all your stuff, editing, resetting, all that. Splitting commits. Interactive rebase can be used to split a commit. So let's say you accidentally made one of those kitchen sink commits and you want to split it into more discrete components. Simply mark that line as E for edit, and the rebase will stop at that point. It'll reset the log to the previous commit, leave the changes in the working tree. When it stops, you should reset the log to the previous commit and leave the changes in the current working tree by using git reset head caret. So now that commit has been removed. So you recreate it in the way that you want, possibly splitting it up, breaking it up into multiple smaller commits using the standard git add-p and git commit lather rinse repeat. It's another demo. Looks like we might have some time. So, important things to remember: rebasing is destructive. Make sure you back up. You can always just create a new branch as a backup, or copy the whole repository. It works. Double check which branch you're on. It's so easy to be wrong. And know whether you're up to date. Make sure that you're up to date with whatever the upstream is at. All right, remotes. I'm going to go through this kind of quickly. Basically, we've dealt with the local repositories so far. However, Git supports remote repositories, and several protocols are supported. Git, HTTP, SSH, local file system. For remotes that you authenticate with, you'll often use SSH. And HTTP or Git is often used for anonymous projects. You know, when you clone from GitHub, you'll see the http://github.com/blah whatever. And file system is good for cloning a repo that already exists on your local disk. Git supports multiple remotes. You can push and pull to and from each. This is because Git can detect when repos have a common history. Very easy since you have the SHA-1 hashes or the SHA-1 hashes. Some example cases: the Linux kernel. Public and private repositories. You have a code, you're working on code from your own private repository, but when you want to send it off to the world, push to GitHub. So getting a repository from a remote is called cloning. It's git clone, blah, 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 whatever. SSH syntax requires the public key. Git protocol is anonymous. HTTPS protocol is useful if you're behind a firewall. These commands clone the repository, including all history from the master branch. Cloning a repo gives a single remote called origin. Other remotes can be added. Git add remote, symbolic name, URL. And you can check out branches from remotes. Git check out remote/branch. You can look at what remotes are being tracked using git remote-a. And when you check out a branch from a remote, it'll automatically track the remote from which it came. So if you do git push to send stuff up, or git pull to pull the latest down, it'll do what you expect it to. You can see what branches are available on the remote by doing git branch-a. There's clone with reference, which basically sometimes you might want to make a new copy of repositories that you already have. Use --reference to clone a local repository. It'll use hard links to save space, and cloning will be faster. Fetching remember that your local Git has the capacity to be a complete repository. You know, you can have your own branches, tags, etc. Git fetch will fetch all of the branches, tags, etc. called refs from a remote to your local repository. It will not modify your local copy, or your working copy. Push and pull to get updates from remote. You pull from it. Git pull remote name and the branch. Or a lot of times it's implicit. You can just do git pull. But usually it's best not to do it like this, because if your local branch has local commits, then your history will diverge from upstream, in which case when you do your git pull, Git will do what's called a merge commit, which is probably not what you want. Really, you're better off pulling with FF only, which means that only fast-forward merges are allowed. That means this means that the local repository has no local commits. If it can't fast-forward, it'll just fail. Then you figure out why, fix it, and try again. And again, Git is usually pretty vocal about what's going on, so it makes it easier to fix. All right. Avoiding pull issues. Have your master branch that tracks an upstream. Do your work on local working branches, and when the upstream changes, check out the master. Do a git pull with FF only. Git check out your working branch and rebase against master. And now your working branch is up to date. Pushing is sending your changes, your commits to remote, most often the origin. And when it's time to push, Git checkout master, make sure your master is updated from remote. Then merge your working directory and push. Sometimes you don't have push access. Usually this is the case for open source projects. In this case, you'll send patch files to the maintainer, and Git makes this pretty easy to do. Git format-patch makes a nicely formatted patch file that you can send off to, to the maintainer. You can also make it also makes cover letters, including statistics. Be sure and edit it before sending. And then you can even, Git will even use your configured mail client to send it, doing git send-email. Pretty cool. If you're submitting upstream patches, see this excellent talk. And if you are the maintainer, you can accept patches using git am. This will append a set of patches into your commit history, and it does preserve the author name that's present in the patch that you got sent. All right, reflog. Reflog is something pretty cool. Git keeps track of when branches change, whether it's by commits, pulling, merging, whatever. This information is stored in the reflog. Each change gets an entry into the reflog, and the repository can be reset to that state. And the reflog is stored locally, is not pushed. And to see it, run git reflog, shows all the entries and their SHA-1 hashes, which is a different hash than the commit hash, by the way. And to reset a repository to a previous state, do git reset. The reflog is great if you mess up a rebase or a pull, just reset to a known good state. It can be kind of tricky to find the last good state. Just be careful, pay attention to the messages that Git gives you. And most importantly, the reflog is not guaranteed to exist forever. It can be garbage collected at any time using git gc. And in some cases, Git can be set up to automatically run garbage collection. Yeah, don't depend on reflog. Basically, it's there as a sort of an emergency safety net. Now we get to bisecting, which is super cool, especially on larger projects. I mean, you could have a few thousand commits go by before noticing, oh crap, X broke, or whatever. How do you determine where the bug was introduced? Git helps you with, it's this really cool thing called bisecting. Basically, it performs a binary search. So you give it a known good revision and then the bad revision, and tell it to start. And what it'll do, say this is the bad one, and this is the good. But I'll do it from your point of view. Say this is the bad revision. Say this is the known good revision, but this is the bad revision. So Git will basically pick a point in the middle and check that out. You build it, try it. If it's good, then you tell Git that it's good. If it's bad, then you tell Git that it's bad. So let's say it's bad. Well, that means that the bad change happened somewhere between the known good state and here. So then Git will basically take the middle of that. And it's basically binary search algorithm. And it makes it super easy to find where stuff broke. It's really cool. It lets you find the error in O log n, or O log squared n, where n is the number of commits. You can search 1,000 commits in roughly 10 steps. Super efficient and super cool. So to start, git bisect start, then give it a good revision and bad revision. Then Git will start the bisection. It gives you the center commit. Test it, build it. If it's great, if it works, say git bisect good. If it's bad, git bisect bad. Then they'll give you another commit to test. Lather, rinse, repeat. Excuse me. Eventually, it'll tell you where the first bad commit is. This is the one where the bug is introduced. When you do that, when you get there, run git bisect reset. It's a lot easier than it sounds. During a bisect, Git can potentially give you any revision in the history to test. And this is why it's very important that every commit build, run, and pass tests. I mean, imagine a situation where bisect gives you the commit before an oops commit. Yeah, that wouldn't be very fun. This is also why it's important that history be linear and, older commits not depend on newer ones. Teamwork. A lot of, these are the tools to enable large distributed teams of developers to work together, rebasing, cheap local branches, multiple remotes. And this really gets started out because the Linux kernel developers needed a effective way to collaborate, and the Linux kernel team is probably one of the largest software teams in the world. So, this is a great example of eating your own dog food. Typical method, each developer has their own online repository. Developers work on code, push it to their own repositories. When it comes time to submit code to the maintainer, the developer uses interactive rebase to linearize and clean up their commits. Usually this happens on a new branch. Once the new branch has been rebased and is cleaned, the developer pushes to the branch to their own public repository, and then sends a pull request, which isn't the same thing as what GitHub calls a pull request. Basically, a pull request is typically an email that says something like, "Hi, please pull from URL," and then the maintainer can pull this branch into their own local repository. They can look at the changes using the git log, and even if the developer's branch is based on a revision older than what's on the maintainer's master, it still works. In fact, this is probably the likely case. And of course, Git recognizes the common history and shows only the developer's commits. The maintainer will provide feedback. Developer can integrate the suggested changes using rebase-i, submit another pull request. Maintainer can then repull the branch, review, and merge. And the advantages, code review is possible. Code can be reviewed at the commit level before commits are actually made in the upstream master. Commits can be modified by the developer an unlimited number of times before merging, and this improves code quality. And of course, the maintainer has complete control of the repository, no surprise commits. Last thing I want to talk about today is branching methodologies. With all these great tools, the old saying, with great power comes great responsibility. You don't want to be creating branches willy-nilly, especially if you're working in a team. You want to settle on a standard for how you manage branches and tags. So, yeah, get your branching right. And I don't know why that's a blank slide. Okay, so. And I apologize that this is so small. In the links section that I'm about to get to, I'll provide the link to all this. So for traditional large software projects, fairly slow releases, this is a good branching model. Is this: you have a master branch, and the master branch is basically untouchable. You don't do anything on the master branch. You do everything on developer branch and on a developer branch, and each developer branches off from the development branch, does a feature, fixes a bug, works on a feature, whatever, merges back to the development branch, and periodically when you want to cut a new release, merge development into master, tag the release, boom, you're done. The only way that master should ever be touched is to have stuff merged into it. So that's great for large projects, but what about smaller projects like web apps? Frequent releases, very much moving target. You don't need to get that complex. In fact, it's kind of counterproductive. Much simpler way is just to use master. Whenever a developer wants to fix a bug, add a feature, just branch off of that and then merge back to master. Yeah, so resources. Pretty much the Git Bible is a book called ProGit. It's available online. There's also a great website called Git Ready and man pages. Git has great exhaustive man pages, and to reference a particular man page, you use git dash command. So for example, if you want to read the merge man page, you do man git dash merge. Branching models, which I just talked about, those are the two. They have some really good articles on there. Integrating Git with Bash. One really cool thing is, that I find really helpful is you're able to integrate Git with Bash. So for example, let me show you. So for example, here's one of my repositories. Notice I have whatever branch I'm on as part of my Git, my Bash prompt, and then don't know why it's not working, but if it were working, Git Bash integration also lets you do tab completion, but you can get that at that site. And finally, Alan's great presentation, the OG. There's a video and there's slides, and that's about it. And I think unfortunately, my time is just about up. Check out Alan's presentation. Check that out. He runs through all the Git demos. It's pretty cool. Anyways, are there any questions? I think I have a few minutes. Go ahead. Yes. Every time you put a change in, depending on how you have your configured the prompt for your password. Right. Unless you have flags in that configuration where you can tell not to. Yes. That was a real problem one time. I couldn't figure out how to stop the thing from prompting me. Yeah, Git. There's a global configuration called .gitconfig. And one of the things that you can do in there is you can do set up what's called a key store, and that's a facility local to Git that stores your passwords and stuff, so you don't have to enter your password every single time. Anyone else? Go ahead.
Is it worth, because in my current project, I didn't actually know, like for example, I didn't know you were supposed to have every commit be testable and workable. Do you think it's worth revising every single one of hundreds of old commits to fit this mold?
I mean, I don't know. It depends. If you're talking about a huge project, probably not. But I would definitely start adhering to the conventions from going forward. But yeah, for a large project, it might be a little more trouble than it's worth. Anyone else? I can't see you if you raise your hand, so go ahead. So the question was if you can tell who has their branch checked out. Is that was? And you can't, and that's one of the things to get used to in the distributed model. It's not like Subversion, where when someone checks out a branch, it's sort of locked to them, which is kind of a pain. So yeah, there's no real way of telling who has checked stuff out. You just have to wait till the pull request. Anything else? All right, I think we're good. Thank you so much for coming.